In this video, we'll be looking at Chapter 10, Section D on the unit circle. Now the circle I have drawn is centered at the origin, and it has a radius of exactly 1. And this is known as the unit circle. This circle has an equation of x squared plus y squared equals 1. Now let's say we pick a point P somewhere in the first quadrant of this circle, and P has coordinates A, B. Now if we draw a line between the origin and P, and then we drop a vertical line down to the positive x-axis, we see that we've formed a right triangle. Let's take a look at that right triangle in a little more detail. We know that the hypotenuse has to be 1 because the radius of the circle is equal to 1. We know that the x, or the horizontal leg of this triangle, has to be equal to A because A is the x-coordinate of point P, and likewise the height of this triangle has to be B because the y-coordinate of point P is B. Now if we call this angle theta, we can find the cosine and sine of theta. We know that the cosine is equal to the adjacent side over the hypotenuse, which in this case is A over 1, which simplifies to just A. And the sine of theta is equal to the opposite side over the hypotenuse, which in this case is B over 1, which equals B. But what we're really saying is that cosine theta is equal to the x-coordinate of point P, and sine is equal to the y-coordinate of point P. And this is not only true for points and angles in the first quadrant, but for any point along the unit circle. If we know the coordinates of that point, we know the cosine and sine automatically of the angle that is made with the origin in that point. Therefore, using the original equation of this unit circle, we can plug in the new values of x and y. Therefore, we know that the x-coordinate is equal to cosine. So I'm going to plug that in for x, and I get cosine squared theta plus the new value for y squared, which is going to be sine squared theta equals 1. And this is our very first trig identity. And this is always true for any value of theta. And it has been derived simply from the unit circle. This is a diagram of the unit circle, which shows the angles from 0 to 360 in increments of 10. And we know it's the unit circle because if we look at the cardinal points, we see that there are combinations of zeros and ones, which means that the radius of this circle is 1. This diagram allows us to better visualize what we were talking about in the previous slide, which was that the x and y coordinates for any point on the unit circle are really equal to the cosine of the angle and the sine of the angle that are formed between the origin and that point. So let's take the angle 30 as an example. Well, let's see if we can calculate the x and y coordinates for 30 degrees. First, let's fill in a little bit of missing information here on the diagram. We know that point 5 is right here. This is 0. I'm dealing with the x-coordinate coordinates right now. So this guy right here is 0.6, this is 0.7, this is 0.8, this is 0.9, and we can see that 30 degrees lies between 0.8 and 0.9, and if we count carefully, we see that it's between the third and fourth column, and so we can estimate this x-coordinate to be about 0.87. Now the y-coordinate's a little bit easier. If we can go straight across, and it looks like it's dead on 0.5. So what this tells me is that the cosine of 30 degrees should be about 0.87, and the sine of 30 degrees should be 0.5. Now if you go ahead and check that with your calculator, you'll see that's exactly the case. So you may be asking, why even bother showing you this? Why can't we just use our calculator to find cosine 30 and sine 30? Well, this is where cosine and sine come from. So it's always good to know what your calculator is doing behind the scenes. And in the case of cosine and sine, this is what it's doing. In other words, your calculator is finding the x and y coordinates of the point on the unit circle for the angle that you type in. And there is one more thing I should point out here on the unit circle. Notice that 0 degrees is on the positive x-axis, and that we positively increase our degrees counterclockwise. This is different than bearings, where bearings 0 degrees is up here, and we go clockwise. So that's a very important distinction to make as we're switching from bearings to degrees here. 0 degrees is positive x, and we go counterclockwise for positive angles. Let's take a look at our unit circle again, with center at the origin and radius 1, and we'll pick a point P, and we can draw a line from the origin to point P. But now, this time, let's extend it beyond the circle, and from the point where the circle intersects the positive x-axis, let's draw a line straight up. Notice how we've drawn another right triangle. And if this is still theta, we can now define tangent theta in more detail. We'll call this point T and this point A. And now we know that tangent theta is equal to opposite over adjacent. So in this case, tangent theta is equal to the length of TA divided by 1, because the radius of the circle is 1 here. So tangent is defined as the length of this line for any point on the unit circle. And you can imagine as we go around the unit circle, that line will change. As we get closer to the x-axis, that line gets very much smaller. And as we get farther away from the x-axis, that line gets very big, approaching infinity. So that's the definition of tangent. That's where tangent comes from. So tangent theta is the length of the tangent line from the x-axis to the extension of line OP. Let's take a look at a few examples. In these problems, it's given that theta is between 0 and 180 degrees, and we want to solve these equations to one decimal place. In all of these problems, it's helpful to draw a unit circle, a quick sketch of the unit circle, and I'll show you why. Now for the first problem, we have cosine theta equals 0.623. But remember from our previous slides that the cosine is actually equal to the x-coordinate of the point that forms the angle theta with the origin. Well, if this is the x-coordinate must be positive, and therefore it must be on the right side of the unit circle. Let's estimate that x value here. And if we drew a line vertically through that x value, we'd see that it intersects the unit circle in two places. That's because there are two angles between 0 and 360 that would have this same x-coordinate. However, it's given that theta must be between 0 and 180 degrees, which is only the top half of the unit circle. So I'm really interested in this value right here and not this one just yet. That tells me that my answer should be somewhere between 0 and 90 degrees. Now, we actually know how to solve this problem. We can isolate theta using the inverse cosine. We can use our calculator, and it will tell us that theta is approximately equal to 51.5 degrees, which makes sense because that angle is in the first quadrant. The next example is cosine theta equals negative 0.317. So let's again draw the unit circle here. And remember, cosine is the x-coordinate, which in this case is negative, so I'm going to be on the left-hand side of the unit circle. And again, there are actually two possible choices here, but one of the choices would put theta outside the range of 0 to 180. So I'm going to solve this problem the exact same way as I did the previous one. We'll use the inverse cosine. I can plug this into my calculator, and make sure your calculator is in degree mode. And we get theta is approximately 108.5 degrees. And this makes sense based on the unit circle that we saw. We know we're staying between 0 and 180 degrees, and 108 degrees is just past 90, so we're on track here. And so far, the unit circle seems to be nothing more than a check in these problems, but when we start dealing with sine here, you'll see that it's actually pretty important that we check our work with the unit circle. So in this case, we're looking at sine theta equals 0.814. And again, we're dealing only with angles between 0 and 180 degrees. But remember now that sine is actually the y-coordinate. So I'm going to move up from the origin, 0.814. And if I draw a line through 0.814 on the y-axis, you'll see that I hit the unit circle twice, and both of these produce angles that are between 0 and 180 degrees. So in this case, I'm going to actually get 2 answers. Now, if I solve this problem in the same way that I did before, where I isolate theta and I use the inverse sine, and then I plug this into my calculator gives me 54.5 degrees. However, that's only one answer. And so if you take nothing else away from the video, remember that often when we're dealing with sine between 0 and 180 degrees, there's usually 2 answers, and your calculator only gives you one. That's why we need the unit circle here. So what's the other angle? What's this guy right here? Well, we can find that out pretty easily using some symmetry here. We know that this angle right here has the same value as theta, and if this is 180, then this angle is simply 180 minus theta, which in this case is 125.5 degrees. This method also becomes important for cosine when there are no restrictions placed on the angles. So, in other words, if we're dealing with angles between 0 and 360, then in this case, there are two possible solutions. And again, your calculator is only going to give you one. So make sure you're understanding the parameters of the problem and what the possible answers are.